It's somewhat backwards, but we're ending this chapter on equilibrium with LeChatelier's principle, which essentially is the driving force for equilibrium. And LeChatelier's principle says that when you apply stress to a system in equilibrium, you cause the system to change to reestablish equilibrium. So, in other words, if I have too many products, the reaction will shift to form reactants. If I have too many reactants, the reaction will shift to form more products. So I'm trying to reduce the stress on the system to shift away from an area where there's too much towards an area where I need more. There's several ways that I can stress an equilibrium system to cause it to change. First way I can do that is change concentration. So if I add more reactants to a constant volume, if I remove some reactants or some products, I'm changing the concentration of one of the species. I can change the pressure. I'm dealing with gases. Third thing I can do is change the temperature. Now if I change the concentrations, if I change the pressure of constituents in a reactant, the equilibrium constant doesn't change. But if I change the temperature, the equilibrium constant changes. Why is that? Because temperature is considered either a reactant or a product, depending if I'm talking about an endothermic reaction or an exothermic reaction. Again, how the equilibrium constant is changed depends on whether the reaction is endothermic or exothermic. And if you know which it is, you can predict which way the K will change, whether the equilibrium constant will get bigger or whether the equilibrium constant will get smaller. And we'll take a look at some examples of that in class. If we take a look at this reaction one more time, so nitrogen plus hydrogen going to ammonia, and we look at it in terms of gas in a constant volume container, we have our nitrogen molecules here. We have our hydrogen molecules here. And so we have a specific number of them. We also have a couple of ammonia molecules here. So we have all three particles present. Now we add ammonia. No, we don't. We add nitrogen. So we're increasing the amount of nitrogen, increasing the concentration or the pressure of nitrogen. Which way should it shift the reaction? I hope you said that it shifts it to the right, because we're adding a reactant, so we're going to cause the reaction to shift this way and form more ammonia. So if we take a look now, we have more ammonia molecules than we did before because we've added a reactant. We can do a similar type of thing by changing the volume. Now we're not adding particles, we're just changing the volume in which they exist. The equilibrium here is going to shift, not because I'm changing number of moles, but because I'm looking at pressure and actually moles of each thing. So here I have 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. So my total number of moles of reactants is 4. My total number of moles of products is 2. So when I increase the pressure, I give the particles less space, I increase the pressure on all of them, the reaction's going to want to shift to minimize that pressure effect. So if I have 4 particles on the reactant side and 2 moles of particles on the product side, my reaction is going to shift so that I get more moles of products, so I reduce the number of moles of particles from 4 to 2. So if I take a look, my moles of ammonia are here, 2, and I increase it, and now I get more moles of ammonia, significantly more moles of ammonia, because the nitrogen and the hydrogen have combined, reducing the total number of moles of particles in the container, which reduces the overall pressure. That takes us all the way through equilibrium. We have a lab that will give us examples of this, and we'll take a look at a variety of these examples in more detail.